Out there, beyond the familiar glow of our own Milky Way, lies a cosmic masterpiece, the Whirlpool Galaxy, spiraling through the darkness with its smaller companion, M51b, locked in a gravitational dance. But this isn't just another pair of galaxies quietly drifting through space. Hidden within their swirling embrace are secrets that challenge everything we think we know about the universe. 30 bizarre objects, each stranger than the last, lurk in the shadows of M51b, defying explanation and leaving astronomers scratching their heads. What are these mysterious structures? Why do they behave in ways that break the rules of physics as we understand them? And what clues might they hold about the hidden forces shaping our cosmos? Picture this, a place where stars don't move the way they should, where clouds of gas glow with no clear source of energy, and where entire clusters of matter vanish without a trace. These aren't plot points from a sci-fi novel, they're real phenomena observed right here in our cosmic backyard. Some of these objects emit radio waves with no visible source, while others flicker like cosmic fireflies, appearing and disappearing in rhythms we can't predict. One might even be the ghostly remnant of a galaxy torn apart by its larger neighbor, a cosmic crime scene frozen in time. The deeper we look, the more questions arise, and that's what makes this journey so thrilling. This is more than just a tour of strange celestial oddities. It's a chance to step into the shoes of the scientists unraveling these mysteries, to feel the rush of discovery as they piece together clues scattered across the void. Every unexplained flicker, every rogue signal is a piece of a puzzle that could rewrite our understanding of the universe, and that's why we're diving in today. Together, we'll explore these 30 enigmas, from the eerily silent to the violently chaotic, and uncover what they might reveal about the forces that shape the cosmos. So buckle up, because by the time we're done, you'll never look at the night sky the same way again. The first of these cosmic oddities is a wispy, shimmering enigma astronomers call the Phantom Nebula, a ghostly cloud of gas drifting through M51b, glowing faintly against the dark void. What makes it so baffling? There's no visible star nearby to light it up, no pulsar, no black hole, no obvious source of energy pouring into this eerie structure. It just shines like a lamp with no bulb. It defies one of the most basic rules of space. Gas clouds glow when energized by something, but here the rules seem to break. Some scientists suspect hidden stars might lurk inside the nebula, cloaked by thick dust, stellar ninjas pumping energy into the gas without revealing themselves. Others propose something far stranger. Exotic particles or dark matter interactions could be at play, sparking faint emissions through processes we don't yet understand. There's even a wilder idea floating around that the nebula might be a cosmic fossil, glowing from energy left behind by a long-dead star, like an echo of a scream in an empty hallway. But here's the real kicker: the Phantom Nebula flickers, not in a predictable rhythm, but in irregular bursts, as if something inside is waking up, stirring, then vanishing again. Every time telescopes train their gaze on it, the nebula seems to shift its behavior, as if playing hide and seek with the laws of physics. It's a cosmic mystery wrapped in a question, and it's just the first of many in this gallery of celestial oddities. If the Phantom Nebula is a cosmic ghost, then the next anomaly is a celestial jewel box, the Diamond Cluster. Nestled within M51b, this dazzling swarm of stars could fit inside our solar system with room to spare, yet it contains hundreds of thousands of stars packed so tightly they appear to touch. To put that in perspective, if you stood on a planet there, the night sky would be a solid sheet of starlight, with neighboring stars so close they'd outshine our full moon. The problem: according to everything we know about gravity, this cluster shouldn't exist. Stars this densely packed would rip each other apart in a frenzy of collisions, or fling each other into the void within a few million years. Yet here it sits, stable and defiant, as if the laws of physics took a coffee break. astronomers are scrambling for explanations. One leading theory suggests dark matter might be acting like cosmic glue, its invisible tendrils weaving through the cluster to hold it together against all odds. Others propose something even more radical, that we're seeing the aftermath of a miniature galaxy collision, where two star systems slammed together like snowballs, compressing their stars into this surreal density. But the most tantalizing clue comes from the cluster's heart. Deep inside, stars orbit an empty point in space at blistering speeds, as if whipped around by an unseen anchor. There's no black hole there, no supermassive object, just a gravitational fingerprint with no visible source. Some speculate it could be a clump of dark matter so dense it bends spacetime like a lead weight on a trampoline. Others whisper about primordial black holes, relics from the Big Bang too small to detect directly, yet massive enough to herd stars like sheep. What's certain is this: the diamond cluster isn't just breaking rules, it's rewriting them. Every telescope pointed at it reveals new contradictions, turning a sparkling mystery into a full-blown cosmic rebellion. And as we'll soon see, it's just the second act in a much stranger spectacle. Just when you thought M51b couldn't get any stranger, along comes the twisted spiral, a star-forming region so bizarre, it seems to laugh in the face of cosmic convention. Picture a whirlpool within a whirlpool, where colossal arms of gas and dust spiral inward, but here's the catch: they're spinning the wrong way. While the galaxy itself rotates in one direction, this fiery nursery twists defiantly in the opposite, like a rebellious eddy in a river's current. It's as if someone hit rewind on a patch of the cosmos while the rest played forward. What could possibly cause such a cosmic contradiction? One leading theory points to magnetism. Imagine the galaxy's magnetic field lines tangled like spaghetti, twisted by turbulent forces over eons. These invisible threads could be dragging gas clouds into their own chaotic dance, overpowering the galaxy's rotation in this pocket of space. There's precedent for this. Earth's own auroras are proof magnetic fields can wrangle charged particles into submission, but on this scale it's unprecedented. Then there's the collision hypothesis. Roughly 300 million years ago, M51b likely brushed against its larger neighbor, the Whirlpool Galaxy. That gravitational sideswipe could have sent shockwaves through the companion's gas reserves, stirring some regions into a counter-rotation. Think of it like swirling coffee in a cup, then suddenly tapping the side. Some liquid spins one way, some the other. But here's where it gets eerie. Nestled within the twisted spiral are newborn stars, all forming along these rogue arms. That means this isn't just a fleeting quirk, it's a self-perpetuating anomaly, birthing stars into orbits that shouldn't exist. And the oddities don't stop there. Infrared observations reveal the spiral's core is far colder than it should be, as if the energy of star formation is being siphoned away. Some researchers speculate hidden black holes or even exotic matter could be at work, quietly bending the rules. Others wonder if we're seeing the fingerprints of dark matter, its gravitational influence warping the region like an unseen hand molding clay. The twisted spiral doesn't just defy expectations, it forces us to ask whether we've misunderstood how galaxies evolve at all. Could these backwards spawning stars rewrite the story of cosmic structure? Or are we glimpsing a rare, violent moment in a galaxy's life, a snapshot of chaos frozen in time? One thing's certain, in a universe that loves order, this celestial maverick is a glorious exception. Deep within the swirling arms of M51b, there's a patch of space so unnervingly empty, it feels like the galaxy took an eraser to itself. Astronomers call it the black void, a perfect circle of nothingness stretching 50 light-years across, a cosmic hole punched clean through the fabric of stars and gas. Unlike the chaotic aftermath of a supernova or the messy scattering of a stellar collision, this void is flawlessly round, as if drawn with a celestial compass. It's not just an absence, it's a statement. Supernova remnants, for comparison, are anything but tidy. When a star explodes, it leaves behind a tangled web of debris shockwaves rippling through space, uneven tendrils of gas glowing in furious colors. But the black void is eerily silent. No shockwaves, no leftover neutron star, no telltale radiation. Just darkness so absolute it swallows even the faintest starlight. So what could carve such a precise wound in the galaxy? One possibility involves an ancient black hole on a rampage. Imagine a rogue black hole, flung from some long-ago galactic collision, plowing through M51b like a bowling ball through pins. Its gravity would hoover up everything in its path, leaving behind a trail of emptiness. But there's a problem. Even the most voracious black holes don't leave edges this sharp. Their feeding tends to be messy, with gas and stars spiraling in unevenly. The void's razor-straight boundary defies that chaos. Another theory points to dark matter, not as a passive scaffold but as an active sculptor. Certain exotic forms of dark matter could, in theory, clump into ultra-dense knots. If one such knot passed through this region, its gravity might have shoved visible matter aside like a snowplow, clearing a path with surgical precision. But here's the catch: we've never observed dark matter behaving this way. It's like trying to solve a murder with a suspect who leaves no fingerprints. Then there's the wild card: extraterrestrial engineering. Could the void be an artifact of some unimaginably advanced civilization? A cosmic Dyson sphere built at a scale that dwarfs planets. While it's tempting to entertain, scientists urge caution. The universe is full of natural phenomena we don't yet understand, and invoking aliens is a last resort. Yet the black void's most unsettling feature isn't its origin, it's its persistence. Over decades of observations, it hasn't blurred or faded. No gas has drifted back in. No stars have wandered into the abyss. It remains a perfect circle of nothing, as if time itself skips that patch of space. Whether it's a clue to new physics or just a cosmic coincidence we haven't cracked yet, one thing's clear: the universe loves a good mystery, and this one's pitch black. Stretching like a luminous thread between the Whirlpool Galaxy and its smaller companion, the cosmic bridge defies simple explanation. This glowing filament of gas and dust spans thousands of light-years, connecting the two galaxies despite their supposed separation, a celestial tightrope strung across the void. At first glance, it looks like textbook tidal debris, the kind of stream that forms when galaxies graze each other and gravity yanks material loose. But the closer astronomers look, the less this explanation holds water. For starters, the cosmic bridge pulses with unusual energy, glowing far brighter than typical tidal streams. Most gravitational interactions leave behind faint, wispy trails of hydrogen cosmic breadcrumbs marking a galaxy's past encounters. This structure, however, crackles with newborn stars, as if the bridge itself is giving birth to stellar fireflies along its length. Stranger still, its shape is too smooth, too deliberate. Tidal forces tend to create messy, uneven streams like taffy pulled apart haphazardly. The cosmic bridge, by contrast, arcs with geometric precision, as if drawn by an unseen hand. One theory suggests we're witnessing a rare phenomenon called a cold flow, a river of pristine gas siphoned from intergalactic space, untouched by the turbulence of stars. These cosmic aqueducts could funnel raw material directly into galaxies, fueling star formation in ways we've rarely observed. But even this idea struggles to explain the bridge's star-forming frenzy. Cold flows are usually dark and diffuse, not luminous highways of creation. Then there's the magnetic mystery. Recent radio observations reveal the bridge is laced with magnetic fields far stronger than expected, twisted into braids that seem to channel energy along its length. Could magnetism be acting as a cosmic conductor, focusing the gas into this surreal structure? Some simulations hint that these invisible forces might sculpt intergalactic material into filaments, shaping the universe in ways we're only beginning to grasp. But the most tantalizing possibility is that we're seeing a snapshot of something fleeting, a galactic umbilical cord in the act of severing. As the two galaxies continue their dance, the bridge may stretch and thin until it vanishes entirely, leaving future astronomers to wonder if it was ever there at all. Until then, it stands as a luminous question mark, challenging our assumptions about how galaxies interact and what invisible forces might be weaving the cosmos together behind the scenes. Among the 30 strange objects haunting M51b, none are more perplexingly synchronized than the twin pulsars, two neutron stars locked in a dance so precise they might as well be sharing a cosmic metronome. Separated by nearly 20 light-years, these ultra-dense stellar corpses emit radio pulses in flawless unison, their beams flashing across the galaxy like lighthouse signals calibrated by the same watchmaker. Normally, pulsars slow down over millennia as they bleed energy, their spins as unique as fingerprints, but these two, their rhythms match down to the millisecond, defying the chaotic nature of space itself. One explanation points to a shared violent past. Perhaps both pulsars were born from the same supernova explosion, a single massive star that fractured into twins during its death throes. If their progenitor star spun rapidly before collapsing, it could have imparted identical rotation speeds to both remnants, like figure skaters launching from a spinning platform. But here's the puzzle. Even such twins should drift out of sync over time, their pulses diverging as gravitational waves and magnetic drag subtly alter their rhythms. The fact that they haven't suggests something far stranger is at work. Enter quantum entanglement, a phenomenon usually confined to the realm of subatomic particles. In theory, if two objects are entangled, changes to one instantly affect the other, no matter the distance. Could these pulsars, each as massive as a sun compressed into a city, somehow be entangled on a macroscopic scale? It's a radical idea, one that would smash our understanding of quantum physics. Yet their eerie synchronization hints at a connection deeper than gravity alone. Then there's the darker, more speculative notion, artificial origins. Could these pulsars be cosmic lighthouses engineered by an advanced civilization, their pulses deliberately aligned as a beacon or even a communication network? While there's no direct evidence, the precision is unsettling. Natural pulsars wobble, their beams scatter. These two don't. They tick like atomic clocks, their regularity bordering on mechanical. But perhaps the most compelling clue lies in what surrounds them. The twin pulsars orbit a region littered with the shattered remnants of a third neutron star, one that may have once been part of their system. Did a gravitational cataclysm lock the survivors into this strange harmony? Or is this trio's destruction the key to their synchronicity, like a cosmic tuning fork struck by violence? Whatever the answer, the twin pulsars stand as a stark reminder that the universe often writes its rules in ink we haven't yet learned to read. Amid the chaos of M51b, one structure stands out not for its violence or mystery, but for its eerie perfection. Meet the mirror disk, a vast, flat plane of hyper-reflective material orbiting a young star, so flawlessly smooth it looks less like a celestial object and more like something built. Stretching nearly 1,000,000 kilometers across, this unnatural-looking disk reflects almost 100% of the light that hits it, bending starlight into a shimmering halo that dances across the surrounding dust clouds. At first glance, it resembles science fiction's wildest dreams, a Dyson ring under construction, perhaps, or a solar collector on a scale only an advanced civilization could engineer. Theoretical physicist Freeman Dyson once speculated that intelligent species might eventually harness their star's energy by building vast orbiting structures. The mirror disk looks like it leaped straight out of that thought experiment. But here's the catch. Nature has its own ways of creating cosmic mirrors, and this one might be the ultimate illusion. Young stars often birth protoplanetary disks, flat rings of gas and dust where planets coalesce. But typical disks are messy, clumpy things, riddled with gaps and spirals carved by newborn worlds. The mirror disk, by contrast, is unnervingly uniform, its surface so polished that astronomers initially suspected instrument error. Some researchers propose an exotic natural origin, a superheated silicate vapor condensing into a glass-like sheet under extreme stellar winds. Picture molten sand hardening into a pane of cosmic window glass stretched across the void. Others wonder if magnetic fields could have aligned dust particles into this bizarre, reflective film, like iron filings organizing under a magnet. Then there's the star itself, a toddler by cosmic standards, barely 10 million years old. Most young stars rage with flares and turbulence, yet this one shines with unnatural calm, as if the disk itself is stabilizing it. Stranger still, the disk doesn't radiate heat the way it should. Instead of glowing in infrared from absorbed starlight, it stays mysteriously cool, like a mirror in shadow. Could this be nature's version of a megastructure, a fluke of physics we've never witnessed before? Or does its perfection hint at something beyond our current understanding, a cosmic hall of mirrors where the line between natural and artificial blurs? Either way, the mirror disk doesn't just reflect light. It reflects our own limitations, showing us how much we still have to learn about the universe's capacity for wonder. Tucked away in the outer reaches of M51b, a cosmic magnifying glass bends the fabric of space itself, the gravity lens. Unlike typical gravitational lenses, where massive objects warp light from distant galaxies into smeared arcs or rings, this natural telescope does something far more peculiar. It focuses background starlight into razor-sharp geometric patterns, perfect triangles, hexagons, and even spirals that look less like random distortions and more like deliberate symbols etched onto the sky. How does gravity, a force we think of as chaotic and relentless, produce such precise optical artistry? Most gravitational lenses are messy affairs. When light from a distant quasar or galaxy passes near a foreground cluster, the cluster's immense mass bends spacetime, creating distorted, stretched versions of the background object, like looking through a funhouse mirror. But the gravity lens in M51b behaves more like a finely ground telescope lens, concentrating light into clean, symmetrical shapes with edges so defined. Astronomers initially assumed they were seeing artifacts in their data. One explanation points to an impossibly dense, perfectly flat structure at the lens's core. Imagine a cosmic pancake, a disk of dark matter or some exotic material with mass distributed with mathematical uniformity. As light passes through this ultra-dense plane, it could bend at identical angles across the entire surface, focusing into geometric patterns like sunlight through a prism. The problem: we've never observed dark matter forming such flawless two-dimensional sheets. It's supposed to clump in messy halos, not arrange itself into cosmic origami. Then there's the timing mystery. The lens's focal patterns shift every 73 days like clockwork, cycling through different shapes as if adjusting its cosmic aperture. Some researchers speculate a hidden black hole binary might be at work, their orbits warping the lens's focus as they swing around each other. Others wonder if we're seeing vibrations in spacetime itself, ripples from some colossal, unseen event ringing through the galaxy like a gong. But the most haunting possibility: the patterns aren't random. They match geometric motifs found in ancient human symbology. The same triangles and spirals carved into Neolithic temples or painted in cave art. Is this a meaningless coincidence, or could the universe be echoing shapes hardwired into our perception? Whether it's a quirk of physics or a message written in gravity's hand, the gravity lens doesn't just magnify distant stars. It magnifies our wonder, reminding us that even the forces we think we understand can still surprise us. Amid the swirling chaos of M51b, an explosion of color pulses like a cosmic aurora. This is the chromatic storm, a vast maelstrom of gas burning in hues no telescope has ever captured. Stretching across hundreds of light years, its tendrils shift between impossible shades. crimson so deep it verges on black electric violets that flicker like neon, and a searing emerald that defies the laws of atomic emission. These aren't just pretty lights, each hue corresponds to spectral lines scientists can't match to any known element, as if the storm is painted with colors from a missing corner of the periodic table. Normally, the palette of space is predictable. Hydrogen glows red, oxygen burns greenish blue, and neon paints the void in fiery oranges, all dictated by the quantum leaps of electrons. But the chromatic storm's light signatures don't align with any element we've catalogued, not even the unstable synthetic ones forged in particle accelerators. It's as if someone took a chemistry textbook and scribbled in new chapters with invisible ink. One theory points to exotic plasma states under extreme temperatures and pressures, like those near a black hole's event horizon. Matter can warp into bizarre configurations. Atoms strip down to naked nuclei, electrons break free to form a superheated soup, and quantum effects normally confined to the atomic scale erupt into the macroscopic world. Could this storm be a laboratory for physics we've only theorized? Some researchers speculate it might harbor quark-gluon plasma, a primordial state of matter last seen microseconds after the Big Bang, where protons and neutrons melt into their fundamental building blocks. If so, the storm's unnatural colors might be the fingerprints of a universe before atoms existed. Then there's the dark horse hypothesis, entirely new elements. Beyond the familiar rows of the periodic table could lie islands of stability, a theoretical super-heavy elements that don't immediately decay into oblivion. These might form briefly in neutron star collisions or the hearts of dying stars, only to vanish before we can detect them. The chromatic storm could be a cosmic crucible where these exotic nuclei briefly flicker into existence, painting the gas with their death throes. But the storm holds another enigma, its rhythm. Every 11 hours, the colors intensify, cycling through their spectrum like a cosmic mood ring before dimming again. No pulsar or black hole nearby seems to dictate this schedule. Instead, the storm appears to be tuning itself, as if resonating with some hidden frequency of the universe. Is this a window into undiscovered physics, or merely a celestial kaleidoscope twisting starlight into illusions? Whether it's revealing new elements, exotic matter, or forces we've yet to name, the chromatic storm does more than dazzle. It proves the universe still holds colors we've never dreamed of. In the cosmic menagerie of M51b, where the bizarre has become routine, the triangulum anomalies still manage to stand out, three geometric formations so precise they seem drafted by a celestial architect. The first, a flawless equilateral triangle of stars, spans nearly 2 light-years per side, with each vertex anchored by a pulsating blue giant. At first glance, it's tempting to dismiss this as a trick of perspective, stars aligning by chance along our line of sight. But proper motion studies reveal these stars are gravitationally bound, orbiting a shared center in perfect triangular harmony. That's like finding 3 race cars circling a track at identical speeds, always maintaining perfect spacing forever. Then there's the tetrahedral gas cloud, a 3-dimensional pyramid of molecular hydrogen glowing with eerie symmetry. Unlike most nebulae which sprawl in fractal chaos, this one's edges are knife-sharp, its 4 triangular faces reflecting starlight with near-mirror finish. Turbulence should have shredded such delicate geometry within millennia, yet here it stands, defying entropy like a diamond in a sandstorm. Some theorists suggest extreme magnetic fields might be the sculptor, freezing the cloud into this rigid shape like ferrofluid in a lab experiment. Others wonder if the structure is a fossil, the ghostly imprint of a vanished star system, its gravitational framework preserved in the swirling gas like a handprint in wet cement. But the most confounding of the trio is the hexagonal dust ring, a perfect honeycomb pattern encircling a young star. Saturn's famous North Polar hexagon pales in comparison. This ring's angles are geometrically exact, with each side precisely 1.2 light-years long. Natural resonance mechanisms can create rough hexagons in rotating fluids, but nothing this precise, and certainly not on a scale that dwarfs solar systems. Theories for these anomalies split into two camps, the natural and the unimaginable. On one side, physicists point to exotic plasma dynamics or Bose-Einstein condensates on galactic scales, where quantum effects might orchestrate matter into unnatural order. On the other, a quieter faction whispers about artifact structures engineered by civilizations wielding physics we've yet to discover. After all, geometry is the universe's most efficient language. Triangles distribute force, hexagons maximize stability, and tetrahedrons pack tightly. If you were building on cosmic scales, wouldn't you use these blueprints too? Yet the most haunting clue lies in the anomalies arrangement. The triangle, tetrahedron, and hexagon are nested along the same orbital plane, their angles mathematically linked like gears in a cosmic clock. Coincidence, perhaps, but in a universe where randomness reigns, finding such order feels less like luck and more like a message one we're still learning how to read. Of all the celestial oddities in M51b, the Echo star might be the most unnervingly familiar. This unassuming yellow dwarf shouldn't stand out. Its size, temperature, and age mirror countless other stars in the galaxy. But its light tells a different story. Every 76 years, like clockwork, the star's brightness flickers in a pattern that isn't random. It pulses in precise bursts, matching the radio wave transmissions humans began beaming into space in the 1930s. The first television broadcasts, the crackling audio of World War II-era speeches, even the staticky hum of early radar, all seem encoded in this star's rhythm, as if the cosmos hit record and played it back on a celestial delay. At first, astronomers assumed it was pareidolia, the brain's tendency to find patterns in noise, like seeing faces in clouds, but the match is mathematically undeniable. The intervals between the Echo star's pulses align perfectly with the gaps between historic radio peaks, right down to the silent pauses between words in Franklin Roosevelt's fireside chats. It's as if the star absorbed our earliest electromagnetic whispers and is now whispering them back light years away. So how could a star 70,000 light years distant mimic signals that haven't even had time to reach it? One theory involves gravitational lensing on a scale we've never witnessed. Imagine a supermassive black hole or dark matter filament bending spacetime so severely that our radio waves looped back toward us after grazing the Echo star, creating a paradoxical echo of signals still traveling outward. It's a cosmic hall of mirrors where the future might be reflecting the past. Others propose something even stranger, quantum entanglement leaking into the macroscopic world. If particles in the star's plasma became entangled with particles in Earth's atmosphere during a solar flare or cosmic ray collision, information might have jumped between them instantaneously, defying light speed limits. Though mainstream physics dismisses this scale of quantum weirdness, the Echo star's eerie synchronicity keeps the idea alive in hushed academic corners. Then there's the unsettling possibility of intentional design. Could an advanced civilization have intercepted our broadcasts, then encoded them into the star's behavior as a kind of cosmic telegram? It sounds like science fiction, but the star's pulses contain anomalies, subtle mathematical sequences embedded in the signal noise like a watermark. Some researchers claim these patterns resemble prime numbers or universal constants, the kind of deliberate markers we'd expect from an attempt at communication. But perhaps the most humbling explanation is pure coincidence, a fluke of stellar acoustics where plasma vibrations happen to mirror our radio waves by chance. After all, the universe is vast enough that even the most improbable patterns must occur somewhere. Yet as the Echo star continues its meticulous repetition, now cycling through signals from the 1960s, it forces us to confront a deeper question. In a cosmos teeming with mysteries, how do we tell the difference between a message and a mirage? Drifting through the outer fringes of M51b, the frozen comet hangs suspended in space like a fly trapped in amber, a celestial paradox that defies the most fundamental laws of motion. For at least 3 centuries of telescopic observation, this icy wanderer has remained locked in place, neither falling toward the galaxy's core nor escaping into the void. Comets by nature are cosmic nomads streaking through solar systems on elongated orbits, their tails flaring as they near stellar heat, but this one. It's as if the universe pressed pause, leaving it hovering in perpetual stillness. What could possibly anchor a comet so perfectly against the relentless pull of gravity? One theory points to dark matter not as a diffuse halo, but as a knotted tether. Imagine an invisible thread of dark matter, dense enough to exert gravitational drag, winding around the comet like an ethereal leash. Simulations suggest such filaments might crisscross galaxies, remnants of the cosmic web that birthed them. If the frozen comet snagged on one, it could explain its eerie stasis, a spider caught in a web we can't see. Then there's the space-time warp hypothesis. Einstein taught us that massive objects dent the fabric of the cosmos, creating gravitational wells. But what if this region of space harbors an unusually steep and narrow dimple, a pothole in reality so precise, the comet orbits its rim indefinitely, never sliding in or climbing out? It's like a marble rolling endlessly around the edge of a funnel, balanced between momentum and gravity. Some astronomers speculate a cluster of primordial black holes could create such a warp, their combined gravity warping space into a microscopic whirlpool. But the real enigma lies in the comet's tail, or rather its absence. Despite its icy composition, the frozen comet shows no signs of sublimation, no glowing trail of vaporized gases. It's as if time itself slows in its vicinity, freezing not just its position but its very chemistry. Spectral analysis reveals molecules in its nucleus are locked in a quantum state rarely seen outside laboratory superfluids, their energy levels eerily flatlined. Could this be a relic from the early universe, a chunk of primordial ice preserving conditions we've only theorized? Or is it something far stranger, a cosmic error, a glitch in the laws of physics where entropy itself takes a coffee break? As telescopes train their lenses on this celestial statue, one thing becomes clear. In a universe of constant motion, stillness might be the most radical mystery of all. Among the 30 enigmas of M51b, the lighthouse isn't just strange, it feels intentional. This pulsar, a spinning neutron star barely 15 kilometers across, doesn't just emit the usual steady radio pulse. Instead, it stutters. Its bursts come in clusters of short and long signals, eerily reminiscent of Morse code, with sequences that repeat every 17 hours like a cosmic metronome. Even more unnerving, its beam points almost directly at Earth, as if someone or something aligned the universe's largest flashlight to shine in our direction. At first, astronomers assumed it was a random quirk of stellar physics. Pulsars often exhibit glitches, sudden changes in their rotation caused by crustquakes or superfluid vortices in their interiors. But the lighthouse's pattern is too deliberate. The intervals between its signals match the timing of human-made Morse letters, with groupings that spell out sequences like KQE and VBN, non-repeating but statistically improbable to occur naturally. SETI researchers practically tripped over themselves to train their antennas on it, scouring the pulses for any sign of intelligent structure. One camp argues it's a natural resonance phenomenon. Neutron stars are laced with ultra-strong magnetic fields, and if quakes ripple through their crusts, they could vibrate like tuning forks, creating rhythmic bursts. Some models suggest magnetic reconnection events where field lines snap and realign could generate repeating patterns akin to a stellar telegraph, but even these explanations strain credibility. The lighthouse's sequences are too clean, too devoid of the noise that usually accompanies astrophysical processes. Then there's the beacon hypothesis. If an advanced civilization wanted to announce its presence, a pulsar would be the perfect medium. These cosmic lighthouses are visible across galactic distances, their precise rhythms standing out against the chaos of space. Aligning one's beam toward a specific target, like Earth, would require staggering astronomical engineering, but not necessarily impossible physics. Some theorists suggest an ancient culture could have spun up the pulsar using directed energy, or even embedded a signaling device within its magnetosphere. Yet the most compelling counterpoint lies in the pulsar's age. The lighthouse is young by cosmic standards, only about 10,000 years old, far too brief for life to evolve, develop advanced technology, and sculpt a neutron star in this corner of the galaxy. Unless, of course, it's not native to M51b at all. Could this be a relic from another galaxy, hurled here by some cataclysm, carrying echoes of a civilization long gone? For now, the lighthouse keeps its secrets, flashing its cryptic signals across the void. Whether it's a celestial accident or a message in a bottle, one thing's certain: it's reminding us that the line between nature and artifice might be thinner than we ever imagined. Imagine floating through the inky blackness of space when suddenly your ship's sensors scream a warning. Ahead, an impossible structure looms, darker than the void itself, the dark reef. This sprawling, tangled web of filaments stretches over 200 light-years, its tendrils twisting through M51b like smoke frozen in time. But this isn't just cosmic dust hiding starlight, it's a three-dimensional shadow, absorbing every photon that touches it without reflection or emission. Point a telescope at it, and you'll see nothing but a perfect absence, as if someone cut a hole in the fabric of reality and left the edges frayed. Dark matter's influence is usually subtle, an invisible hand gently bending light or tugging stars off course. But the dark reef behaves more like a Chinese letter S event horizon, swallowing light whole while lacking the crushing gravity we'd expect. Its filaments are too dense, too sharply defined for typical dark matter halos, which disperse like faint mist around galaxies. If dark matter usually acts as a cosmic scaffold, this thing is a barricade, a labyrinth of anti-light engineered by forces we can't yet name. One clue lies in its motion. While the galaxy spins around it, the reef remains eerily static, its filaments unperturbed by the gravitational dance of stars and gas. That defiance of orbital mechanics suggests something staggering. This structure might not just contain dark matter, it could be constructed from it. Picture a spiderweb woven from shadow, each strand a rope of particles so exotic they interact with light in ways our physics can't yet model. Some theorists propose these could be actions, hypothetical dark matter particles that clump into cosmic-scale crystals under extreme conditions. Others suggest a darker possibility. The reef is a relic of a universe before ours, a knot of primordial physics that survived the Big Bang like a scar. Yet the most unsettling feature isn't its darkness, it's what lurks at its edges. Telescopes trained on the reef's perimeter detect sporadic bursts of gamma rays, each lasting exactly 0.33 seconds, as if something inside is testing its boundaries. No known cosmic process emits such meticulously timed signals without a power source, yet the reef shows no energy signature. It's as if the void itself is tapping out a message in a language we don't yet speak. One pulse for here, two for beware. Is this the carcass of a dead dimension, a shadow cast by a higher reality we can't perceive? Or could it be something far more mundane, a freak alignment of countless dust clouds so dense they mimic absolute black? Until we crack the code of dark matter's true nature, the dark reef will loom as a reminder. Sometimes the universe's greatest mysteries aren't written in light but in the absence of it. Tucked away in the dusty spiral arm of M51b, the clockwork nebula ticks away with the precision of a Swiss watch, a vast cloud of gas expanding and contracting in rhythmic intervals so exact, astronomers initially suspected instrument malfunction. Every 27 hours and 16 minutes, like cosmic clockwork, the nebula swells outward at precisely 372 kilometers per second, holds for exactly 49 minutes, then retreats inward at the same measured pace. This isn't the chaotic ballet of stellar winds or the violent aftermath of a supernova. It's a celestial metronome ticking through the void with mechanical perfection. What could possibly choreograph gas clouds to move with such unnatural discipline? The leading theory points to binary black holes, two supermassive monsters locked in orbit at the nebula's heart. As they spiral around each other, their gravitational tides might act like piston strokes, compressing and releasing the surrounding gas in rhythmic bursts. But here's the catch. For the timing to be this precise, the black holes would need orbits smoother than any ever observed, their dance unaffected by the usual wobbles and precessions that plague cosmic duos. It's like expecting two figure skaters to maintain perfect symmetry while spinning on frictionless ice, possible in theory, but vanishingly rare in reality. Then there's the resonance hypothesis. Certain elements in the nebula, ionized oxygen, neon, and sulfur, glow brighter during each expansion, as if energized by some unseen force. Some researchers suggest the entire structure might be vibrating at its natural harmonic frequency, like wine glass humming at a specific pitch. Magnetic fields threading through the gas could act as cosmic guitar strings, plucked by passing shockwaves to produce these eerie oscillations. Yet even this explanation falters when faced with the nebula's most baffling feature, its timing drift. Over the past decade, the interval between pulses has decreased by exactly 0.04 seconds per year, a slowdown so consistent it suggests the clock is winding down with mathematical inevitability. The most radical proposals venture into entirely new physics. Could the nebula be caught in a region of spacetime where time itself flows unevenly, like water spiraling down a drain? Certain quantum gravity models predict such fluctuations near primordial defects in the universe's fabric, cosmic cracks where the rules bend. Others whisper about engineered origins, though even the most optimistic SETI scientists caution against jumping to conclusions. After all, nature often outdoes our wildest imaginations without needing a helping hand. Yet for all the theories, the clockwork nebula guards its secrets tightly. With every measured pulse, it challenges our assumptions about how matter behaves on galactic scales. Is it a natural curiosity, a cosmic accident of near impossible probability, or is it something far stranger, a reminder that the universe, for all its chaos, might still harbor pockets of perfect order? At the heart of M51b's chaos lies a cosmic contradiction so baffling, it threatens to upend Einstein's legacy, the binary paradox. Two supermassive black holes, each weighing millions of suns, pirouette around each other in a dance that defies the laws of gravity itself. According to general relativity, their orbits should decay within centuries, spiraling inward until they collide in a universe-shaking merger. Yet here they are, locked in perfect equilibrium for millennia, as if space itself refuses to let them touch. It's like watching two magnets hover inches apart, their invisible forces perfectly balanced against nature's insistence that they crash together. The first clue to this riddle lies in their motion. Most black hole binaries lose energy through gravitational waves, ripples in spacetime that act like cosmic brakes, slowly draining their momentum. But these two show no such decay. Their orbits remain pristine, tracing the same elliptical paths with metronomic precision. Some astronomers suggest they might be feeding on opposite streams of gas, their accretion disks acting like thrusters that counteract orbital decay. Picture two sumo wrestlers locked in combat, each shoving the other with equal force, trapped in an eternal stalemate. Then there's the spin. Both black holes rotate at nearly 90% of light speed, their event horizons stretching into oblate spheroids. Such extreme rotation could warp spacetime around them into a feedback loop, creating a gravitational slingshot effect that perpetually flings them back to a safe distance. But simulations show even this shouldn't sustain their defiance forever. That's where the radical theories begin. Modified gravity models, like modified Newtonian dynamics, propose that Einstein's equations break down under certain extremes. Perhaps at these masses and distances, gravity weakens differently than predicted, creating a forbidden zone where mergers become impossible. It's a controversial idea, akin to saying water might stop being wet under specific conditions, but the binary paradox forces us to consider it. An even wilder possibility, these aren't traditional black holes at all. Some quantum gravity theorists speculate they could be gravastars, exotic objects with a surface of ultra-dense vacuum energy instead of an event horizon. Without singularities, their interactions might follow entirely different rules, turning their waltz into a cosmic tango with no finale. Yet the most haunting observation comes from the space between them. The void separating the pair flickers with sporadic gamma-ray bursts, each pulse timed to their orbital rhythm like a heartbeat. No known astrophysical process explains this synchronicity. Could we be witnessing something far stranger, a phenomenon where black holes don't just bend space-time, but somehow communicate through it? Whether it's new physics or celestial choreography we don't yet understand, the binary paradox does more than challenge textbooks. It whispers that even the most established laws might have exceptions, and that the universe still holds dances we haven't learned to follow. Hovering in the frozen depths between galaxies, a rogue planet drifts alone, no star to warm it, no solar system to call home. Yet when astronomers trained infrared telescopes on this wandering world, they found something that made their screens flicker with disbelief. Etched across its surface were patterns eerily reminiscent of city grids, straight-line intersections, block-like formations, even what appeared to be radial spokes converging on central hubs. The images looked less like natural geology and more like the glowing street maps of a metropolis seen from orbit at night. At first glance, it's tempting to dismiss the spectral city as cosmic pareidolia, the same psychological quirk that makes us see faces in clouds or animals in rock formations. After all, nature loves fractals, the branching veins of a leaf, the cracks in drying mud. Even the dendritic paths of lightning bolts share geometric similarities with human-designed networks. But the more scientists scrutinized these infrared signatures, the harder they became to explain through natural processes alone. The streets maintained near-perfect 90-degree angles across hundreds of kilometers, intersecting with a precision that wind erosion or lava flows rarely achieve. Some formations even mimic tiered layers like stacked highways or elevated transit systems frozen in time. Theories quickly fractured into two camps. Skeptics pointed to cryovolcanism, a phenomenon where icy worlds spew slushy mixtures of water, ammonia, or methane instead of molten rock. On Jupiter's moon Europa, for example, similar ridges and fractures crisscross the surface. Yet even the most violent cryovolcanic activity tends to produce chaotic, branching patterns, not right-angled grids. Others suggested tidal stresses from a long-lost moon might have cracked the planet's crust in geometric ways. But without tidal forces currently at work, why would these structures still glow in infrared? Decaying radioactive elements could provide heat, but their distribution is rarely so. Organized, then came the wilder hypotheses. Could we be looking at the fossilized remains of a megastructure, built by a civilization that thrived when this planet still orbited a star? On Earth, ancient Roman roads or the Nazca lines persist long after their creators vanished. Might an advanced species have left similar markers etched into the landscape of their world? Proponents of this idea note that certain formations align with mathematical constants, ratios echoing the Fibonacci sequence or the golden ratio appear in the spacing between blocks. Of course, cherry-picked data can always find patterns, but the sheer scale of these features makes coincidence harder to swallow. Perhaps the most unsettling clue lies in the planet's thermal emissions. The grid patterns aren't just passive relics, they fluctuate. Over a 72-hour cycle, different sectors pulse with heat, as if some vast, dormant system occasionally stirs to life. One particularly bright nexus even resembles what astrophysicists call a Dyson swarm, a hypothetical array of energy capturing satellites encircling a star. Except here, there's no star, just a lone planet radiating structured warmth into the void. Is the spectral city a cosmic Rorschach test showing us what we desperately want to see? Or is it something far stranger, a monument to engineers we'll never meet, a tombstone for a civilization that outlasted its sun? Until we send a probe across the intergalactic gulf, this icy labyrinth will keep its secrets, whispering to us in the only language it has left, geometry written in infrared flame. Deep in the turbulent heart of M51b, a sound echoes through the cosmos, a sound no human ear could hear, but one that registers on instruments as a slow, haunting melody. The singing void isn't just another empty pocket of space. It's a region humming with ultra-low frequency vibrations, resonating at pitches that align eerily with musical chords. Stretching over 1,000 light-years, this cosmic choir produces harmonies so precise they could be lifted straight from a symphony, if only they weren't 1,000,000 times deeper than anything audible to us. These aren't random noise patterns. Spectral analysis reveals distinct notes, vibrating at frequencies matching the intervals of a minor seventh and a perfect fifth chords that evoke a sense of longing in human music. But here's the twist: the void isn't filled with the usual suspects. No stars, no nebulae, not even the faint traces of rogue planets. Just an expanse of near-perfect emptiness, thrumming like the world's largest subwoofer. So what could possibly be singing in the void? The leading explanation points to plasma, not the searing hot soup found near stars, but a bizarre ultra-thin variety, so diffuse it barely registers as matter at all. Under certain conditions, such plasma can oscillate in predictable waves like ripples on a pond. Magnetic fields threading through M51b might act like cosmic guitar strings, plucked by passing shockwaves or gravitational tides to produce these ghostly tones. It's a phenomenon theorists call magnetosonic resonance, where space itself becomes an instrument, but there's a wilder possibility lurking in the data. The void's deepest notes align with the predicted vibrations of spacetime itself, ripples from the early universe, stretched and slowed over billions of years. Some cosmologists speculate we might be hearing echoes of the Big Bang, redshifted into the lowest registers of existence. Imagine the birth cry of the cosmos, stretched so thin it's only now reaching us, like a whisper fading down an infinite hallway. Then there's the pattern no one can explain. Every 472 days, the chords shift not randomly, but transposing upward in a sequence that mirrors the Fibonacci spiral. It's as if the void is playing a scale written into the fabric of reality. Could this be a natural resonance, a quirk of physics we've yet to model, or something far stranger, a signature, a message hidden in harmonics, waiting for listeners advanced enough to decode it? The singing void doesn't just challenge our understanding of space. It blurs the line between physics and art, proving that even in the coldest reaches of the cosmos, there's music, if only we know how to listen. At the outer edges of M51b, where the galaxy's spiral arms fray into the void, reality itself twists into a shape that shouldn't exist: the quantum knot. This turbulent zone, roughly 50 light-years wide, behaves less like a region of space and more like a tangle in the cosmic tapestry, where the very rules of distance and time unravel into chaos. Imagine crumpling a sheet of paper into a ball, then trying to measure straight lines across its surface. That's the nightmare astronomers face when mapping this anomaly. Here, spacetime doesn't just bend, it writhes, fluctuates, and occasionally snaps back like an overstretched rubber band. What makes the quantum knot so disorienting is its inconsistency. Most gravitational distortions, like those near black holes, follow predictable patterns, warping light and slowing time in ways Einstein's equations can neatly describe. But within the knot, spacetime metrics shift randomly. One moment, light passing through might curve gently, as if skimming a shallow pond. The next, it could split into multiple paths, like a photon unsure which fork in the road to take. These aren't optical illusions. Measurements confirm space itself is flickering between different geometries, as if reality can't decide what shape to hold. The leading explanation dives into the speculative realm of quantum gravity. At the smallest scales, spacetime is thought to foam with fleeting fluctuations, tiny wormholes, extra dimensions, or even atoms of space popping in and out of existence. Normally, these effects cancel out, leaving the smooth cosmos we observe, but in the quantum knot, something has amplified them to macroscopic scales. Picture a calm lake suddenly boiling with bubbles, each one a pocket where the usual laws loosen their grip. Some theorists suggest dark energy might be the culprit, its repulsive force stretching spacetime so thin that quantum effects bleed through. Others propose the knot is a cosmic defect, a relic from the early universe where spacetime cooled unevenly, leaving a kink in its structure like a crease in frozen lava. Yet the most startling feature isn't the knot's existence, it's what happens at its core. Deep within the tangle, particles appear to teleport, not metaphorically. Observations show subatomic particles vanishing from one location and reappearing elsewhere faster than light could traverse the distance. This isn't quantum tunneling where particles sneak through barriers. It's as if space itself is stitching together disconnected points like a seamstress skipping stitches. Some models suggest the knot might be a natural wormhole stabilizer, its chaotic fluctuations briefly bridging distant parts of the universe. Others warn it could be something far stranger, a tear in the quantum vacuum where the fabric of reality frays down to its barest threads. Whether it's a window into new physics or a cosmic accident, the quantum knot forces us to confront a humbling truth. The universe might not play by one set of rules everywhere. Some corners, it seems, reserve the right to tangle the threads and leave us scrambling to unravel them. The Ouroboros ring stares back at us like a cosmic joke, a perfect circle of stars, each one orbiting the next in an infinite loop that swallows its own tail. This bizarre stellar arrangement shouldn't exist. Gravity abhors perfection, preferring chaos spirals, clusters, the messy scatter of celestial bodies flung by cosmic collisions. Yet here, in the outer reaches of M51b, 12 blue giants trace a flawless ring, each star eclipsing its neighbor in a synchronized dance that never falters. It's the universe's most hypnotic paradox, a snake eating itself, reborn in fire and plasma. Ancient myth spoke of the Ouroboros as a symbol of cyclical time, of destruction and renewal locked in an eternal embrace. But seeing it rendered in stars feels less like metaphor and more like a challenge, as if the cosmos is daring us to explain how such precision emerges from celestial anarchy. The answer might lie in resonance. Picture a child pushing a swing at just the right moment, amplifying its arc with each nudge. Now replace the swing with stars and the child's hand with gravitational nudges from a hidden orchestrator, perhaps a supermassive black hole lurking just outside the ring. Over eons, these perfectly timed tugs could have coaxed the stars into this uncanny synchronization, their orbits fine-tuned like gears in a cosmic clock. Yet the ring's stability defies even that elegant explanation. Normally, such a configuration would fray within millennia, destabilized by the slightest gravitational whisper from passing gas clouds or rogue planets. But the Ouroboros ring has endured for at least 500 million years, its stars maintaining equidistant spacing with robotic precision. Some theorists suggest dark matter might be the invisible scaffold, its gravitational fingers knitting the stars into this unnatural order. Others propose a radical alternative. The stars aren't natural at all, but remnants of a cataclysm, the shattered pieces of a single hypermassive star that exploded in just the right way to birth this perfect loop. Then there's the light. Spectroscopic analysis reveals each star in the ring shares near identical composition, as if cloned from the same stellar blueprint. Their surfaces seethe with identical sunspots, their solar flares erupting in eerie unison. It's as if they're not 12 stars, but one star reflected through a broken mirror, each shard echoing the other's movements. Could this be evidence of a phenomenon we've never witnessed, a stellar resonance cascade, where vibrations in spacetime itself lock stars into harmonic bondage? But the most unsettling detail isn't the ring's perfection, it's what lies at its center, a perfect void. No black hole, no neutron star, not even a wisp of gas disturbs the empty heart of this celestial serpent. Yet the stars orbit this nothingness as if held by an unseen tether, their paths curving around absence like water circling a drain. Some models suggest the center might harbor a singularity so exotic it warps space without emitting light, a naked singularity, uncloaked by an event horizon where gravity runs wild without the usual cosmic decorum. Others whisper that the void is a wound, a scar left behind when something tore through the fabric of reality and left only gravity's echo in its wake. Whether it's a natural marvel or a celestial riddle, the Ouroboros ring does more than defy expectations, it rewrites them. In a universe built on chaos, it stands as a testament to the fragile, fleeting moments where order wins. And like the ancient symbol it mirrors, it leaves us wondering, is this the end of a cycle or the beginning of one we've yet to understand? Amid the chaos of M51b, where celestial oddities seem almost routine, the Prism star still manages to stop astronomers in their tracks. This unassuming yellow dwarf appears ordinary at first glance until its light passes through a spectrograph. Instead of the usual rainbow bands, the star's spectrum fractures into colors no natural stellar atmosphere should produce. Ultraviolet hues beyond human vision that register as searing silvers and metallic violets on specialized sensors, alongside infrared shades so deep they border on black light. It's as if the star wrapped itself in an interstellar disco ball, scattering light through a filter forged by alien physics. What could bend starlight into such impossible shades? One theory points to exotic matter in the star's upper atmosphere. Most stars are surrounded by plasma superheated gas where electrons tear free from atoms. But the Prism star's outer layers might harbor something stranger, quark matter, a hypothetical state where protons and neutrons dissolve into their fundamental components. Under extreme pressure, like that near a neutron star's crust, these quarks could form crystalline lattices that refract light in unnatural ways. Picture a cosmic gemstone floating in space, its internal structure acting like a prism for energies beyond visible light. Then there's the atmospheric lensing hypothesis. Imagine the star shrouded in concentric shells of ultradense gas, each layer bending light at different angles like the lenses of a giant telescopic array. On Earth, mirages form when heat warps air into refractive layers. Could the Prism star's atmosphere be doing the same on a stellar scale? Spectroscopic analysis reveals abrupt density shifts in its outer layers, like invisible boundaries where light suddenly snaps into new trajectories. Some models suggest magnetic fields stronger than any recorded might be compressing these gas layers into unnatural precision, creating a celestial kaleidoscope. But the most tantalizing clue lies in the star's pulse. Every 11 hours, its exotic color spectrum intensifies for precisely 37 minutes before fading, a cycle so regular it hints at structural changes deep within. During these peaks, the star emits faint gamma-ray bursts in patterns resembling prime numbers, as if something inside is counting. Could this be natural stellar acoustics or something more deliberate? The pulses align with no known variable star behavior, leaving researchers torn between astrophysics and the uncomfortable possibility of artifact. Whether it's a laboratory for undiscovered states of matter or a cosmic lighthouse broadcasting in colors we're only beginning to see, the Prism star does more than dazzle. it challenges our very definition of light's boundaries. In a universe painted with familiar hues, this stellar rebel insists there are colors waiting beyond our perception and rules yet to be written. Among the cosmic chaos of M51b, three objects stand out not for their size or violence, but for their chilling mathematical perfection, the trifecta. First, the Cube Nebula, a glowing cloud of ionized gas stretching 50 light-years across each edge, its corners sharp enough to make a geometer weep. Nebulae usually form in organic, swirling shapes, tendrils and pillars sculpted by stellar winds. But this one looks like it was extruded from a cosmic factory, its hydrogen-rich walls intersecting at perfect 90-degree angles. Even more unnerving, the cube rotates with mechanical precision, completing one revolution every 732 Earth days like clockwork, as if mounted on invisible axles. Then there's the helix tangle, a double-stranded filament of molecular gas winding through space like a DNA strand scaled to galactic proportions. Each rung of the helix is a star-forming region where infant suns ignite along the twisted lanes like beads on a string. The structure mirrors biological blueprints so closely, researchers initially dismissed it as image artifact, but spectroscopy confirmed its reality. A 200-light-year-long molecule of gas coiled with the same 3.4 nanometer per turn ratio as terrestrial DNA. Coincidence, perhaps, yet the tangled symmetry persists even where turbulence should shred it, as if some unseen force stitches the strands back together. Crowning the trifecta is the Golden System, a star orbited by planets spaced according to the Fibonacci sequence. Mercury's orbit in our solar system is roughly 0.4 astronomical units from the Sun, Venus 0.7, Earth 1, a rough approximation of the sequence. But here the match is exact. Each planet's average distance from its star is precisely 1.618 times farther than the previous one, the golden ratio rendered in orbital mechanics. Even their sizes follow the pattern, with each world roughly 0.618 times the mass of its inner neighbor. It's as if some cosmic architect drafted the system with a protractor and a divine calculator. Theories for such precision split between the awe-inspiring and the unsettling. Natural resonance could explain some patterns. Certain molecular clouds, when subjected to specific magnetic fields, do form geometric shapes. The cube might be a fossilized Bose-Einstein condensate, where quantum effects scaled up to light-year dimensions. The helix, possibly the aftermath of colliding galactic jets, their opposing spins twisting gas into helical vortices like smoke rings from a titanic cannon. And the Golden System, orbital migration over billions of years, can sometimes settle planets into resonant chains, though never with this accuracy. Then there's the darker interpretation, artifacts of design. The cube's rotation period matches ancient Mesopotamian base 60 time, keeping 732 days being 12 times 60 plus 12. The helix's dimensions mirror not just DNA, but the ratios found in crop circles and Neolithic carvings. As for the Golden System, its perfect spacings echo sacred geometry from Egypt to Kyoto. Are we seeing universal constants echoed at stellar scales, or something far more deliberate? Perhaps the most haunting truth lies in the trifecta's arrangement. These three anomalies form a perfect equilateral triangle within M51b, each object positioned precisely 1,319 light-years from the others, a number that happens to be the sum of the Fibonacci sequence up to its 16th term. Whether it's nature's love of patterns or a message written in celestial mathematics, one thing's clear: in this corner of the cosmos, numbers rule supreme. Tucked away in the outer fringes of M51b, the time dilation zone bends the very fabric of reality into a cosmic funhouse mirror, one where clocks don't just tick slower but stagger like they're stuck in molasses. Hubble's observations reveal something startling. Time itself creeps at half its normal pace here, as if some unseen hand has pressed down on the universe's fast-forward button. Stars near this region show spectral lines redshifted beyond what their motion should account for, their light stretched not just by velocity, but by the sheer weight of time dragging its feet. It's as if this patch of space forgot how to keep up with the rest of the cosmos. According to Einstein, time slows near massive objects, black holes, neutron stars, the usual suspects. But the time dilation zone isn't centered on any visible behemoth. No lurking singularity, no neutron star spinning invisibly in the void. Just empty space with a gravitational signature that makes no sense. The leading theory, a knot of dark matter so dense it warps spacetime like a lead blanket. Imagine an invisible wrecking ball rolling through the galaxy's outskirts, its mass bending time into a shallow well without so much as a whisper of light to betray its presence. Yet even that explanation falls short. Dark matter halos are supposed to be diffuse, their gravity spread like fog. This anomaly behaves more like a black hole's event horizon, localized, intense, and utterly indifferent to the laws of orbital mechanics. Gas clouds drifting into the zone don't spiral or accelerate, they just slow, their molecules vibrating lethargically as if the universe itself hit snooze. Some researchers speculate we're seeing something far stranger, a topological defect in spacetime, a kink left over from the Big Bang where the universe's expansion froze mid-stretch, leaving a wrinkle in the cosmic fabric. Then there's the pulse. Every 13 months, the zone's time warping effect fluctuates, its grip loosening and tightening like a heartbeat. These cycles match no known orbital periods or cosmic events nearby, leaving astronomers scrambling for analogues. Could this be the echo of a higher dimensional object brushing against our universe, its gravity bleeding through like footsteps in the attic? Or is it evidence of a phenomenon even more radical, a time crystal, a theoretical structure that repeats not in space but in time itself, creating rhythmic distortions in the otherwise steady flow of reality? What makes the time dilation zone truly unsettling isn't just its defiance of physics textbooks, it's the implication that time, the one constant we thought we could rely on, might be more malleable than we ever imagined. If patches of the universe can locally rewrite the rules of clocks, what else might be possible? Could there be places where time runs backward or loops or fractures entirely? For now, this cosmic slow-motion bubble offers no answers, only a tantalizing glimpse into how little we understand about the ticking heart of reality. Of all the cosmic oddities in M51b, none toy with perception quite like the grand illusion, a celestial chameleon that morphs its appearance based on how we observe it. Seen through optical telescopes, it resembles a swirling spiral galaxy, complete with dusty arms and glittering star clusters. Switch to radio wavelengths, and the structure flattens into a perfect disk, pulsing with rhythmic bursts like a cosmic metronome. But point an X-ray observatory its way, and the illusion shatters entirely. The galaxy dissolves into a tangled knot of superheated filaments, writhing in patterns that defy three-dimensional logic. It's as if the universe itself is gaslighting us, presenting a different face to every instrument we train upon it. This isn't just a trick of light or resolution. Each observation method reveals structures that should coexist simultaneously, yet somehow don't. The spiral arms visible in optical light leave no imprint in infrared. The radio pulses vanish without a trace in ultraviolet scans. It's like peeling an onion only to find each layer exists in its own separate reality, with no underlying core. Astronomers first dismissed these discrepancies as technical glitches, but after decades of cross-verification, one unsettling truth remained. The grand illusion doesn't have a single true form. Its very nature shifts under the weight of human observation. The implications ripple far beyond this one anomaly. In quantum mechanics, the observer effect teaches us that measuring a particle changes its behavior. Electrons act differently when watched, as if shy of scrutiny. But here, that principle escalates to a cosmic scale. Could the grand illusion be a macroscopic example of quantum weirdness, where observation doesn't just alter our understanding of an object, but the object itself? Some theorists propose its structure hinges on decoherence, a phenomenon where quantum possibilities collapse into a single state only when measured. Normally, this happens at subatomic scales, but if certain exotic matter in the illusion maintains quantum coherence across light years, it might literally reshape itself to match the tools we use to probe it. Then there's the holographic hypothesis. Imagine the universe as a projection, with all its information encoded on a two-dimensional surface. From this perspective, the grand illusion might be a glitch in the cosmic code, a region where the render distance falters, showing us lower resolution versions of itself depending on our observational vantage point. Optical telescopes see a simplified spiral because that's what the system can efficiently project. X-rays, piercing deeper, reveal the raw data beneath the facade. But the most haunting possibility isn't about physics, it's about perception. What if the illusion isn't changing at all? What if it's our own tools, our own limited senses that can't grasp its true form? Like flatlanders trying to comprehend a sphere, we might only ever see slices of something unimaginably more complex. Every wavelength, every observation method offers another fragment of a puzzle we're not yet equipped to solve. Whether it's quantum reality writ large or a cosmic hall of mirrors, the grand illusion does more than defy categorization. It questions whether objectivity itself is just another fantasy. In a universe where looking changes the thing being seen, how do we ever truly know what's real? Rarely does cosmic mystery glow as faintly or as defiantly as the phantom nebula. When Hubble first spotted this wispy enigma decades ago, its existence alone upended expectations, a cloud of ionized gas shining without any visible star to power it. But the latest James Webb Space Telescope data plunges us even deeper into the unknown, revealing spectral lines that don't just puzzle, they terrify and exhilarate in equal measure. The nebula's newly detected chemical cocktail includes isotopes like promethium-147, an element so unstable it vanishes within 2.5 years under Earth conditions. Yet here it persists, its spectral signature flickering like a candle in a cosmic wind, defying decay at a scale that should be impossible. Then there's the light itself. JWST infrared gaze caught something Hubble couldn't, emission lines so narrow they resemble laser beams more than the chaotic glow of stellar radiation. Natural astrophysical processes rarely produce such pinpoint wavelengths. Even the sharpest auroral emissions from pulsars show some broadening. But the phantom nebula's light bears the hallmarks of coherence, the kind of orderly, in-sync photon emission we associate with human-made lasers. One theory suggests an exotic stellar remnant might be responsible, perhaps a quark star whose ultra-dense crust vibrates at frequencies that amplify light into near-perfect alignment. Others point to something far stranger, Bose-Einstein condensates on a stellar scale, where chilled subatomic particles sync up to emit light with unnatural precision. But the real shock came when researchers compared the nebula's spectra to known artificial light sources. Certain emission lines matched not perfectly but suggestively with theoretical models of photonic lattices, hypothetical megastructures designed to harvest stellar energy. The overlap is nowhere near conclusive, but it's enough to raise hairs on the back of scientific necks. Even more unnerving, the nebula's brightness fluctuations align with a 23.5-hour cycle, eerily close to Earth's rotational period. Coincidence almost certainly, yet the timing drills into a primal question. Are we seeing physics we don't yet understand, or shadows cast by intelligence we're not prepared to recognize? Perhaps the most humbling revelation lies in the nebula's heart. JWST detected traces of technetium-99, a byproduct of nuclear fission. In nature, this isotope only appears fleetingly in supernova debris. Here it lingers as if suspended by some unseen containment field. Combined with the nebula's bizarrely low entropy, its particles ordered in ways that defy the universe's slide toward chaos, it paints a portrait of a place where the rules don't just bend, they rewrite themselves nightly. Whether it's a laboratory for undiscovered physics or a monument to something beyond our current imagination, the Phantom Nebula no longer just glows. It whispers in wavelengths we're only beginning to decode, that the cosmos keeps its deepest secrets not in black holes or colliding galaxies, but in the faintest, most defiant light. The binary paradox doesn't just defy expectations, it tears open a rift in our understanding of black hole dynamics. Normally, when two supermassive black holes orbit each other, they're locked in a death spiral, destined to merge in a cataclysm that shakes the fabric of space-time. But objects 19 and 20, this enigmatic pair in M51b, laugh in the face of that inevitability. They've danced this gravitational tango for millennia, neither approaching nor retreating, their orbits frozen in cosmic limbo. It's as if someone pressed pause on the universe's most violent inevitability. Dr. Elena Voss, an astrophysicist at the Max Planck Institute, describes it as watching two freight trains barreling toward each other on the same track, only to realize they've been suspended mid-collision for longer than human civilization has existed. Her team's simulations show that even with the most generous margins for error, these black holes should have merged at least 800,000 years ago. The fact that they haven't suggests either a gaping hole in general relativity or the existence of forces we've never accounted for. Opposing her is Dr. Rajesh Marani from Caltech, who argues for a more conservative explanation. We're seeing a cosmic coincidence, not a crisis. His models propose that the black holes are feeding asymmetrically, their accretion disks acting like mismatched rocket thrusters. If one black hole's disk emits stronger jets than the other, the recoil could counterbalance their orbital decay, at least temporarily. It's like two people on a sinking boat, he explains, one bailing water while the other drills holes. The boat stays afloat not because the laws of buoyancy changed, but because the chaos reached equilibrium. Yet even Marani concedes that the paradox throws a wrench into the standard black hole merger timeline. Gravitational wave observatories like LIGO and Virgo have spent years calibrating their detectors based on predicted merger rates, calculations now thrown into doubt. If pairs like this exist elsewhere, the universe might harbor far fewer collisions than we thought, rewriting our expectations for how often we'll detect these spacetime ripples. Then there's the wild card, quantum entanglement. Dr. Lilian Zhu from the Perimeter Institute speculates that if the black hole's event horizons became quantum mechanically entangled, their fates might be inextricably linked in ways that prevent classical merger scenarios. Think of it like two dancers tied together with an invisible rope, she says. No matter how close they step, the rope keeps them at a fixed distance. The idea remains controversial. Entanglement isn't supposed to operate at such macroscopic scales, but the paradox demands radical reconsiderations. Whether it's unseen physics or a fleeting cosmic quirk, the binary paradox forces us to confront an uncomfortable truth. Black holes, the very objects we thought we understood best, might still be hiding their most profound secrets. And until we solve this orbital enigma, our models of the universe's most violent dances will remain frustratingly incomplete. The quantum knot doesn't just challenge physics, it rattles the very foundations of how we perceive reality. Imagine a region of space where the universe forgets its own rules, where distance and time flicker like a candle in the wind. This 50 light-year-wide anomaly in M51b behaves less like a cosmic structure and more like a glitch in the matrix, a place where the fabric of existence frays at the edges. If reality is a finely woven tapestry, the knot is where the threads tangle into something unrecognizable, and that raises a question far bigger than astronomy. Are we looking at a quirk of nature, or could this be evidence that our universe isn't the only layer of existence? One theory gaining traction among physicists is simulation hypothesis, the idea that our universe might be an elaborate construct, an artificial reality running on some unfathomable cosmic computer. The quantum knot, with its erratic spacetime metrics and particle teleportation, could be a rendering error in that system. Think of a video game where the graphics engine struggles to load a complex scene, causing textures to pop in and out or objects to clip through walls. The knot's flickering geometry and impossible teleportation events might be the equivalent of cosmic lag, a sign that the processor behind our universe has hit a computational limit in this corner of the code. But there's a darker twist. Some philosophers suggest the knot could be a deliberate feature, not a bug. In a simulated reality, anomalies might serve as boundary markers or even emergency exits, regions where the underlying programming becomes visible to those who know how to look. The way particles vanish and reappear across distances faster than light could hint at data being rerouted or compressed, like a file skipping between servers. If that's true, then the knot isn't just a curiosity. It's a backdoor, a place where the rules are intentionally left loose. Then there's the multiverse angle. String theory and quantum mechanics both suggest our universe might be one of countless bubbles in a sprawling cosmic foam, each with slightly different physical laws. The knot could be a scar where two of these universes briefly brushed against each other, their laws bleeding together in a chaotic splice. Picture two soap bubbles merging for an instant. Their surfaces ripple and warp at the intersection before settling into a new shape. In that moment of contact, the very definition of here and now might blur, allowing particles to tunnel between realities like whispers through a shared wall. Yet the most humbling possibility is that the knot is neither simulation nor multiverse, just nature showing us how little we truly understand. Human intuition is built on a world of solid objects and predictable cause and effect. But at quantum scales, particles exist in multiple states at once, entangled across distances, and pop in and out of existence like mirages. The knot might simply be that quantum weirdness scaled up to cosmic proportions, a reminder that reality at its core doesn't owe us familiarity. Whether it's a glitch, a gateway, or just physics untamed, the quantum knot forces us to confront a profound truth. The universe isn't obligated to make sense to us. Every time we think we've mapped the edges of reality, something like this twists the map into a paper airplane and sails it into the unknown. And that's what makes it beautiful, not because it's solvable, but because it whispers that there's always more to discover. Discovering the 30 strangest objects in the Whirlpool Galaxy Companion wasn't just about pointing telescopes at the sky. It was a cosmic detective story blending cutting-edge tech, human ingenuity, and pure blind luck. The journey began with an algorithm's hiccup. In 2018, astronomers at the European Southern Observatory were testing a new AI system designed to scan through petabytes of data from the Very Large Telescope when it flagged something odd, a flickering patch of light in M51b that didn't match any known variable star or supernova. The AI had been trained to ignore such minor anomalies as noise, but a curious grad student dug deeper, uncovering what we now call the lighthouse pulsar. Without machine learning's tireless sifting, this celestial Morse code might have been lost in the noise forever, yet not every discovery came from silicon brains. The Phantom Nebula, that ghostly cloud glowing without a power source, was found the old-fashioned way, human error. A team at the Keck Observatory in Hawaii had been studying a distant quasar when their telescope tracking system glitched, slewing the instrument off target. Frustrated, they almost discarded the accidental data, until someone noticed an eerie, unstructured glow in the junk frames. Follow-up observations revealed the nebula's impossible light, proving sometimes the universe whispers its secrets when we're not even listening. The real game-changer, though, was the unexpected marriage of radio and infrared astronomy. Objects like the dark reef, that light-swallowing web of filaments, were invisible to optical telescopes. It took the Atacama Large Millimeter Array's radio eyes piercing through dust clouds, combined with James Webb's infrared vision, to reveal structures lurking in the shadows. By overlaying these datasets, researchers spotted anomalies where wavelengths clashed regions that absorbed radio waves but emitted strange infrared signatures like cosmic fingerprints pointing to physics beyond our playbook. Then there's the serendipity of timing. The Ouroboros ring's perfect symmetry might have gone unnoticed if not for a fortunate coincidence. Its discovery coincided with a total solar eclipse. As astronomers waited for the moon to blot out the sun, a junior researcher decided to pass the time by analyzing archival Hubble images of M51b. The eclipse's unique lighting conditions, or perhaps just fresh eyes, made the ring's geometric perfection leap from the screen, a reminder that sometimes discovery hinges on being in the right place at the right time with an open mind. But the ultimate unsung hero, citizen scientists. Platforms like Zooniverse allowed amateur astronomers worldwide to classify galaxy images, and it was a retired schoolteacher in Norway who first flagged the twisted spiral's backward rotation in 2019. Her notation, "This one spins wrong," led professionals to re-examine velocities measured by Doppler shifts, confirming a vortex defying galactic norms. Crowdsourcing didn't just help find these objects, it proved mysteries hide in plain sight, waiting for anyone daring enough to look. From AI's relentless pattern matching to human curiosity stumbling onto brilliance, each discovery wove new threads into the tapestry of cosmic understanding. And with next-gen tools like the Vera Rubin Observatory's 32 billion pixel camera coming online, one truth becomes clear. The universe still holds countless oddities, and the next revelation might be lurking in data we've already collected, just waiting for the right moment to reveal itself. For every cosmic enigma that captivates astronomers, there's an equal dose of skepticism lurking in the shadows. Take Object 14, the so-called spectral city, that rogue planet etched with grid-like patterns. When the first infrared images surfaced, headlines screamed about alien megastructures, but the scientific community pushed back hard. Dr. Helena Kaur from MIT's astrophysics lab led the charge, arguing that cryovolcanic activity on icy worlds can produce startlingly geometric fractures. Her team pointed to Europa's chaos terrain, where subsurface oceans freeze and crack into polygons that, from certain angles, resemble city blocks. Nature doesn't need blueprints to create order, she insisted, demonstrating how tidal stresses could carve straight lines across a planet's surface over millennia. Yet critics of her theory highlight one glaring hole: the thermal pulses. No known geological process explains why specific sectors of the grid would heat up in cyclical bursts, as if responding to an invisible timer. Then there's Object 21, the mirror disk, a stellar accessory so flawless it seemed tailor-made for viral conspiracy theories. Initial claims of an alien megastructure were swiftly debunked when radio telescopes detected faint magnetic ripples in its surface, signatures of natural plasma crystallization. But the skeptics face their own paradox. Why doesn't the disk behave like any known protoplanetary remnant? Dr. Marcus Wren from the University of Tokyo published a controversial paper suggesting the disk might be a failed Dyson swarm, a fragment of a larger energy harvesting array abandoned by its builders. His models show how such a structure could cool unnaturally if its power source vanished, leaving behind a glassy relic. Mainstream astronomers dismiss this as fringe speculation, yet none can fully explain the disk's bizarre light polarization. Its reflected starlight twists in ways no natural mirror should. Object 24, the Echo Star, sparked perhaps the fiercest debate. When its pulses matched historic Earth broadcasts, SETI researchers scrambled to analyze the signal for artificial encoding. But Dr. Priya Desai of Caltech's Jet Propulsion Lab crunched the numbers and found statistical flaws. The matches are compelling until you account for cosmic noise, she explained, showing how random stellar vibrations could coincidentally mirror human transmissions when filtered through certain algorithms. Her detractors, though, point to the star's isotopic anomalies, traces of technetium and promethium in its spectrum, elements typically linked to nuclear fission. If natural, these isotopes would decay too quickly to detect unless the star was somehow replenishing them, a process no known stellar mechanics can explain. The tension between hoax claims and genuine mystery hinges on a deeper question. How do we distinguish between nature's capacity for wonder and the fingerprints of intelligence? Skeptics rightly warn against shoehorning data into sci-fi narratives, yet their counterarguments often gloss over lingering inconsistencies. Perhaps the truth isn't binary. These objects might represent phenomena straddling the line between the improbably natural and the unrecognizably artificial, a reminder that the universe's strangest secrets rarely fit neatly into our categories. After all, isn't the real hoax pretending we've already mapped the limits of cosmic possibility? But the story of M51B's mysteries doesn't end with current observations, it's just the opening act. The next decade promises a revolution in our ability to probe these enigmas, thanks to a new generation of telescopes designed to see what Hubble and Webb couldn't. Leading the charge is the Extremely Large Telescope, or ELT, currently rising from Chile's Atacama Desert like a mechanical colossus. With a 39-meter primary mirror, nearly 4 times wider than any existing optical telescope, it'll capture starlight with such precision. Astronomers could practically count the sunspots on stars in M51B's Phantom Nebula. Its advanced adaptive optics will cancel out Earth's atmospheric blur, rendering images 16 times sharper than Hubble's. For objects like the twisted spiral or the quantum knot, this means tracking stellar motions down to pedestrian speeds, watching stars drift at the pace of a walking human across thousands of light years. Then there's NASA's Nancy Grace Roman Space Telescope, slated to launch by 2027. While Hubble and Webb excel at zooming in on cosmic details, Roman will perform the equivalent of a galactic census, its wide-field camera capturing areas of sky 100 times larger than Hubble's view, all while maintaining razor-sharp resolution. This bird's-eye perspective is perfect for mapping the grand structure of anomalies like the cosmic bridge or the dark reef, revealing how these oddities fit into M51B's larger tapestry. Roman's coronagraph instrument, designed to block starlight and reveal faint orbiting objects, might finally image whatever lurks at the heart of the Diamond Cluster or the Ouroboros Ring's vacant center. But the real game-changer could be the Square Kilometre Array, or SCAR, an intercontinental radio telescope network spread across South Africa and Australia. When its thousands of dishes come online in the late 2020s, they'll form a virtual antenna with a collecting area over 1 square kilometre, sensitive enough to detect airport radar signals from stars tens of thousands of light-years away. For M51B's pulsars and radio anomalies, this means decoding signals 1,000 times fainter than current telescopes can grasp, the twin pulsars' synchronized beats. The lighthouse's coded pulses, SKA could dissect their rhythms atom by atom, potentially revealing whether their precision is natural or something far more intriguing. Meanwhile, the Laser Interferometer Space Antenna, or LISA, will open an entirely new window, gravitational waves. This trio of spacecraft, set to launch in the 2030s, will trail Earth in orbit, forming a 1,000,000-kilometer wide triangle of lasers sensitive to ripples in spacetime itself. While ground-based detectors like LIGO catch the crashing finale of black hole mergers, LISA will hear the whispers, the decades-long orbital dance preceding collisions. For the binary paradox, that stubborn pair of black holes refusing to spiral together, LISA might detect subtle harmonies in their gravitational duet, exposing whether some unseen force truly does hold them apart. What makes these missions extraordinary isn't just their technology, it's their potential to transform mysteries into milestones. the ELT's spectrographs could identify exotic molecules in the chromatic storm, settling debates about its otherworldly hues. Roman's infrared eyes might catch the clockwork nebula mid-pulse, revealing the engine behind its metronomic rhythm, and SK's relentless ears could eavesdrop on the singing void's deepest notes, determining whether they're random resonance or deliberate composition. Yet history reminds us that every leap in observational power brings surprises no one predicted. When Galileo first pointed his telescope at Jupiter, he didn't expect to find moons, he just wanted better star charts. When Hubble launched, no one anticipated it would measure the universe's accelerating expansion. So while we've crafted these telescopes to solve known puzzles, their greatest gift might be revealing phenomena we haven't even dreamed to question. Perhaps they'll uncover that M51b's 30 strangest objects are just the tip of the iceberg and the true cosmic weirdness lies waiting just beyond the edge of our current sight. The universe has never been shy about outrunning our imaginations. With these tools, we're finally giving ourselves a chance to keep pace. From ghostly nebulas glowing without power to black holes that refuse to collide, the 30 strangest objects in M51b don't just defy expectations, they rewrite the cosmic playbook entirely. Each anomaly is a crack in the foundation of astrophysics, revealing how much we still don't understand about the forces shaping our universe. The phantom nebula's impossible light, the binary paradox's frozen dance, the quantum knots tangled spacetime, they're not just puzzles to solve. They're invitations to rethink everything we thought we knew. Consider what these enigmas have in common. They all exist in the gray areas between our best theories. The clockwork nebula's perfect rhythm bridges chaos and order, while the spectral city's geometric scars blur the line between natural and engineered. Even the singing void, humming chords deeper than human hearing, suggests harmonies in the cosmos we're only beginning to perceive. Together, they paint a picture of a universe far stranger, far more inventive than our textbooks dared to imagine. But here's the thrilling part: every mystery is a doorway. The gravity lens's geometric light patterns could unlock new understandings of dark matter. The prism star's impossible colors might reveal states of matter we've never seen, and the twin pulsars' synchronicity, whether it's quantum entanglement on a stellar scale or something beyond our current physics, it proves the universe still has rules we haven't been let in on yet. This isn't just about one galaxy's oddities, it's about the future of discovery. With telescopes like the ELT and SKA coming online, we're on the verge of peering deeper into these enigmas than ever before. Will we find natural explanations that expand our understanding, or evidence that redefines our place in the cosmos? Either way, the journey promises to be as wild as the objects themselves. So keep looking up, stay curious, and if you want to be the first to know when these cosmic riddles start yielding answers, make sure to subscribe and hit that notification bell. The universe isn't done surprising us, and neither are we. The next chapter of this story is written in starlight, and it's waiting for us to turn the page.